We are going to demonstrate experiment on energy gap of a semiconductor. Aim of the experiment: to determine the energy gap of a semiconductor using a PN junction diode. Apparatus required for this experiment: germanium diode, thermometer, copper vessel, oil, regulator power supply, microammeter, heater and connecting wires. Now, formula to find energy gap of a semiconductor here: Eg is equal to 2.303 into slope into K divided by 1.6 into 10 to the power of minus 19 in electron volts. Here K is a Boltzmann constant, and that value here we taken as 1.38 into 10 to the power of minus 23 joule per Kelvin. Theory: the energy gap of a material is defined as the minimum amount of energy required for an electron to get excited from the top of valency band to the bottom of the conduction band. Solids are classified into insulators, semiconductors, conductors. In insulators, there is large energy gap in between valency band and conduction band. In coming to semiconductors, there is a small energy gap in between valency band and conduction band. In conductors, there is no energy gap in between valency band and conduction band. Here we are going to find energy gap of a semiconductor material. It can having a small energy gap that we are going to find. Circuit diagram. The circuit diagram consists of PN junction diode, microammeter and a battery. Here the PN junction diode is connected in a reverse bias. That's why the negative terminal of a battery is connected to positive terminal of a diode, and diode negative terminal is connected to ammeter negative terminal, and positive terminal of ammeter is connected to battery positive. We start our experiment. This is our experiment arrangement. This is a germanium diode here. Here this is a copper vessel. Inside the copper vessel we taken oil, and this surrounded with the heater. This whole arrangement we taken in a wooden box. Here red and black indicates the two terminals of PN junction diode. You can see in a kit three devices here: a battery, it can having as a fixed power supply, and microammeter and heater output connection plug. Now we connect these three devices. Now here the PN junction diode we connect here reverse bias. That's why the positive terminal of PN junction diode is connected to negative terminal of a battery, and negative terminal is nothing but N type is connected to ammeter negative terminal, and remaining positive terminal of ammeter is connected to positive terminal of a battery, and also heater wire we connect the heater output connection plug. Now switch on the mains. Here we see the red light, and we also on the heater button here. Now we observe the temperature in a thermometer is gradually rises, and also observe the current in a microammeter is also increases. Yeah. Here we wait some time. The temperature is showing up to 90 degrees centigrade. It's showing. Now we off the heater connection. Now the temperature is rises again. After some time it will be started to decreasing, and also the current is also decreases. At this situation we note down the readings in observation table: decreasing temperature and decreasing current. Observation table. This is our observation table. Now note down thermometer temperature readings. In first column, temperature in degree Celsius and the corresponding current readings in a micrometer we note down here. Here the temperature we taken 100 degrees Celsius, 90 degrees Celsius up to 40 degrees Celsius to see the micrometer readings and note down the corresponding current readings here. And after that we calculate capital T here. Capital T is temperature in degree kelvins. Now to convert temperature in degree Celsius to degree kelvins we add 273, and next we calculate 1 by T value here, we get 1 by T values here, and next to convert the current in microamperes to amperes and note down here. After next we calculate R is nothing but here resistance. According to Ohm's law, R is equal to V by I. We consider here V is voltage. In our experiment, our battery can having as a 1.5 volts here, and I is nothing but here current in amperes. We substitute here V and I values, we get the capital R values here, and finally we calculate log R values here. In this observation table we consider 1 by T and log R values. Model graph. Now we draw a graph in between 1 by T and log R values. Now we consider 1 by T values on x-axis, log R values in a y-axis. Based on our 1 by T and log R values, we get a straight line here. We consider any 2 points on a straight line. We consider that points as represented by x1, y1 and x2, y2. Now, from the graph, we calculate the slope. For a straight line slope formula, we know that y2 minus y1 divided by x2 minus x1. Now we substitute y2, y1, x2, x1 here. We calculate, we get the slope here. And finally, after we get a slope value, now we using a formula of 2.303 into slope into k divided by 1.6 into 10 to the power of minus 19. Now we substitute here slope value and k value. We get energy gap value is around a 0.7 electron volts. Why? Because here we consider a germanium diode. At last we write the results here. The energy gap of a given semiconductor is around, we get 0.7 electron volts. Thank you.